Well, hello everybody. So, welcome again to the third lecture on adiabatic two-phase flow and flow boiling in microchannels. So, this is the second topic that we are going to cover. In the first topic what we covered, I just gave you a brief introduction regarding multi-phase flows, so that after this it will be easier to grasp the concepts or the reasons why multi-phase flow is different in a macro and a microchannel, right. So, today we will be going through or rather we will be making a journey, or I will be introducing you to two-phase flow through micro devices. Now, the first thing is this current trend of miniaturization. Why has this come into being? Now, there are some specific advantages of miniaturized systems, and the first thing is, as we know that there is an extremely large surface to volume ratio, which will be clear from this particular slide. If you see, we find that your area to volume ratio is inversely proportional to diameter. So, when diameter goes down, this area to volume ratio it increases. Now, what happens as a result of that? Due to this extremely large surface to volume ratio, there is a short transportation path, and naturally that implies a high rate of transport processes. It can be mass transfer, it can be heat transfer, and it also leads to an enhancement of mass transfer limited chemical reactions. So, therefore, as a result of this, firstly due to this fast mixing we have enhanced transport, and then this leads to a more compact device, and therefore, heat transfer can occur across a very less temperature difference. Naturally, when we are dealing with less volume, it automatically implies that there will be a smaller amount of inventories for process development. This is particularly important for two types of materials. One, if the material is very expensive, we require less capital and inventory cost. The other thing is, if we are dealing with hazardous material, it automatically assures an intrinsically safe reactor. And well, less weight, less volume, less power consumption for mobile systems, they go without saying. And also we find that in this particular case, we have a very narrow residence time distribution. The reason for this will be clear as I go further, but due to this narrow residence time distribution as compared to conventional batch reactors or CSTRs. So, therefore, we have a better control on product quality, number one, and number two, it allows high intensity reactions to be precisely controlled for optimum yield and selectivity. And this is particularly useful, as I was just mentioning a few seconds ago. It is particularly useful for the control of fast reactions, which are mass transfer controlled and mass transfer limited, and they give rise to accuracy and explosion concerns when they are performed in stirred vessels. To be specific, these reactions, there are just a few examples I have given. There are many more reactions which are facilitated by performing them in your micro reactors. Few of them are nitration, hydrogenation, sulfonation, oxidation, and so on and so forth. Well, and naturally since we are dealing with a very small amount of fluid, so what it implies, a smaller pump and a lesser pumping power. It also tells you that temperature profiling during course of extraction is facilitated due to the high specific surface area. This is difficult in conventional systems. And another interesting part is, suppose we want to scale it up for a large scale production. Generally, for macro systems, what we do, we increase the dimension of the system, and then we apply several scaling laws to find the dimension of the macro or the large scale system with respect to the pilot plant prototype which has been developed in the laboratory. Now, for micro systems, there is no question or there is no story of increasing the dimensions. So, in this particular case, the concept of scale up comes from numbering up concept rather than scaling up concept. And so, therefore, since for large scale production we go for this numbering up, it reduces the risks involved when transferring technology from the laboratory to the commercial scale, which is always we see as engineers, this scale up is quite a challenge for us. Well, so with all these applications, so therefore, in a nutshell, what do we find? We find that microreactors, they provide a large surface to volume ratio, as a result of which it intensifies different transport processes and also mass transfer limited chemical reactions. or in other words, it leads to process intensification, which signifies not only a large amount of production at reduced cost, but it also ensures safer and a cleaner environment as well. And among the different process intensification techniques, if you find, you will find that miniaturization is one of the techniques that is followed. The primary reason is that just as I have mentioned, the larger your surface area to volume ratio, and in fact, in the introduction I was mentioning, while I was talking about the applications of multiphase flow, I was mentioning that whatever chemical processes we come account, be it reacting systems or in non-reacting systems, all of them they involve multiphase flow, that we have already discussed. All of them they involve the contacting of two phases and then ensuring that one phase is not completely dispersed or as very fine films, so that the maximum transport takes place. And if you observe, you will find both for reacting and non-reacting systems, almost all the process they are intensified by miniaturization. There is just one exception to it. That exception I leave you to guess, but anyhow it will be quite evident to you that the exception is distillation. We do not have a micro distillation column, because there actually we need that particular temperature difference, and so therefore, except distillation, all other processes, be it in reacting systems or in non-reacting systems, they are intensified by miniaturization. So, apart from your microreactors, there are also rather a large number of other applications of miniaturized systems. For example, in compact heat exchangers, nowadays we find that there has been a thrust of excessive cooling, or rather now since we have gone to this miniaturized systems. So, therefore, there has been increased need of studying two-phase flow and heat transfer through microchannels, because of the rapid development of microscale devices which are used for several engineering applications. Now, these microscale devices, they pertain to maybe medical devices, your high heat flux compact heat exchangers as I have shown in this particular slide, and cooling systems of various types of equipments such as high performance microbes, electronics, supercomputers, high powered lasers, and so on and so forth. Now, in these particular applications which demand a good amount of MEMS cooling or microchip cooling or whatever, we will find out that the cooling does not occur by the conventional heat transfer processes like conduction, convection, radiation, etc., due to the very small amount of volume of fluid available. So, the convection currents cannot be set up in that way. But in this particular cases, the chunk of cooling occurs by phase transfer, and so therefore, moment the greater amount of cooling has to occur by phase transfer. Naturally, two-phase flow, a liquid and a vapor flow occurs in these applications. So, unless we understand the distributions or the typical characteristics of two-phase flow, we cannot go for an efficient cooling system. So, this is one part of the application in several types of cooling of compact devices, or in other words this cooling of electronic chips, etc. This is one part. The other part is from the chemical engineering aspects, where we find that microreactors are being increasingly used for production of several chemicals, as I have said, more importantly in the pharmaceutical industries and as bioreactors. Now, in this particular case, the use is primarily because it is very or rather it is possible in this particular reactors to ensure a narrow residence time distribution, so that we have a better control on the product quality. So, with a large number of coupled advantages, high transport characteristics, the narrow residence time distribution, then again we have your this temperature profiling possible, numbering up being possible. So, with all this combined characteristics, we find that microchannels, they are a very good potential area of process intensification, and also for several, rather it serves several new engineering devices which are coming up in the way with the advent of electronics, supercomputers and so on and so forth. Well, now the next thing is that what are the what do you expect will be the differences when the two phases, for the time being let us assume a gas and a liquid phase, say when they are flowing through a large system and when they are flowing through a miniaturized system. Now, whenever there are two phases, they interact due to a large, there is an interaction of a large number of forces. What are the forces that we encounter? One is definitely body force or gravity. Then there is inertial force, definitely in a flow system, inertia is going to be quite important. Then viscous forces can also come into picture, and normally in macro systems these surface tension forces are not very important, but mainly these are the four forces due to which we encounter the different flow patterns. When the liquid inertia is high, it can break the gas phase into small bubbles, and as a result of which we get bubbly flow pattern. Okay, so, inertial dominant flow patterns are bubbly on one side, and on the other extreme what do we have? When gas inertia is sufficient, it forms a gas core and the liquid film is pushed at the sides. So, therefore, generally inertia controlled, we have, if people say inertia controlled regime 1, regime 2, one comprises of bubbly and other dispersed patterns, on the other extreme it is the annular pattern. When gravity is important, what do we have? First thing what we have is stratification in horizontal and near horizontal systems. This is number one. What is the other thing? We have asymmetry in phase distribution, right. So, as long as we are dealing with macro systems, generally if it is a gas liquid system or a liquid liquid system with one of the liquids or rather both of the liquids not very viscous, generally we deal with, rather there is an interaction between body forces and inertial forces. Viscous forces come into being when we are dealing with high viscous oils like crude oil, lubricating oil and something of this sort. Now, whenever we have reduced the dimension, what happens? The first thing which is very evident to you is gravity forces get suppressed. When gravity forces get suppressed, the effects of gravity, they tend to become less, or in other words, there will be lesser and lesser tendency of stratification, or stratification is suppressed, we say. This will be evident from the flow patterns which have been observed by the researchers Kawaji and Chung in a 100 micrometers and a 96 micrometers square and circular channels. You will find it's, I do not know how evident it is, you will find that what we have here is we are having some slug sort of things, and then when the slugs become bigger, then they get bridged at regular intervals, and the gas liquid interface, it is marked by a waviness of smaller amplitude, a periodic interfacial wave, and at regular intervals the gas core, it forms a neck in region where the neck is much more narrow, and there the liquid, it appears to be as a ring. Because the liquid is not very large, or rather the liquid slug is not sufficient, it just appears to form a ring between successive Taylor slugs or Taylor bubbles. So, this is known as liquid ring flow. Then gradually what we have, we find that gradually when the gas velocity increases, naturally the gas flows very fast, and we have, I do not know whether it is clear, we have something of the serpentine like gas code they say. Here in this particular case what we have is more or less it is sort of in this particular way the gas core it becomes thinner and it flows in a serpentine like fashion, but due to the interfacial waviness, but the normal annular flow which we have in macro channels with a gas core and a liquid fill, that does not happen except the gas velocity is very high and the liquid velocity is very low. The concept of stratification being suppressed is also evident from these flow patterns which have been taken in a milli channel or maybe in a millimeter size channel and in a micro channel. Even in a millimeter size channel we find that initially more or less the flow patterns in a milli channel, they are more or less similar to what we had discussed regarding the flow patterns in a macro channel, but there are some additions and deletions. For example, we find that when the gas flow rate is very less, we have a bubbly sort of flow pattern, but definitely this bubbly flow pattern does not comprise of finely dispersed bubbles which we had observed in the for the macro systems. Okay. So, therefore, here the bubbles they are quite elongated, disc shaped or cap shaped, and you will find that unlike horizontal conventional channels, they are more or less distributed uniformly throughout the flow passage, and the tendency of being confined to the upper region is comparatively less. Now, this particular tendency it decreases as the conduit dimension starts decreasing, and after a time we find when the gas velocity is increased, then naturally these bubbles they come very close and they form the plug bubbles like in conventional channels. But this bubbly to plug transition occurs at a lower gas velocity as compared to conventional channels. Number 1. Number 2, if you had remembered the video which I had showed you yesterday, you would have seen how erratic and irregular the Taylor bubble was. While in this particular case we find the Taylor bubble it has a regular shape with a rounded nose and a rounded tail. Well, I can show you a video, I will be showing it to you after some time, where it will be more evident that how rounded the Taylor bubbles are as compared to macro channels. Again you keep on increasing the flow rates, naturally the gas bubbles will get elongated, there will be waviness along the interface etc., etc. And after some time they start coalescing and a flow pattern emerges which the researchers call as churn flow. But let me tell you, this churn flow is distinctly different from the periodic chaotic churn flow which had been observed for large diameter pipes. In this particular case, usually I find that there are 3 types of phenomena associated which people club together, and if they see any of these phenomena, they say it is churn flow. What are the things which happen? One thing is that the bubbles become quite large and they start shedding smaller and smaller satellite bubbles, and therefore, more or less a churning mixture is formed here. The other thing which happens is the bubbles they start getting longer and maybe a churning wave sort of a thing that sweeps the interface, and due to this particular churning wave more or less the interface appears to be irregular, and this particular flow pattern also people are unable to decide what it is. There are long gas slugs, okay. People are almost convinced that well it is the annular flow, and then they find that no, there is some amount of liquid bridging. So, therefore, they cannot define it as slug, they cannot define it as annular. Since there is good amount of waviness at the interface, they call it the churn flow pattern. There is another thing also which people call as the churn flow pattern, which is when the gas plugs, they become quite large, right, and they almost merge with each other, but we find that the gas core, it is marked by a periodic wave. It is sort of this sort of a thing. The gas core, there are large bubbles here, there is a small necking sort of a thing and it goes in this particular way. So, therefore, there is a gas core which is possibly continuous, but there are very short liquid slugs, and these liquid slugs, or rather these liquid chunks, they form a bridging or a necking sort of a thing. It is better called necking than bridging, and this particular thing also people do not know whether it is slug or annular. So, they call it as a churn flow pattern. So, usually we find that churn flow, it is marked by three particular phenomena. The first one is serpentine like gas core, and this is surrounded by a deformed liquid film. Now, here I would like to tell you one thing. Such a serpentine like core used to be observed for when high viscous oil and water used to flow in a circular pipe. I will just show you a slide in order to highlight this particular situation. I will just show you this particular slide, so that it will be easier for you to understand. Let us see this particular slide. Here if you observe, here I have taken the flow patterns of, this one is kerosene water and this one is your lubricating oil water. In this particular situation, if you find a serpentine like a serpentine like lubricating oil core in the central portion, and it is surrounded by a annular water film. And we find that this particular sort of corkscrew waves, or whatever you call it, they are absent for kerosene water flows. In this particular case, you find that such a type of wave, the waves are much more symmetric and they are not asymmetric like this case. So, here we know that this happens because of the high viscosity of the oil, or in other words, viscous forces are responsible for this. So, from there we can very well conclude that the situation that we had got for this particular case as well also arises because of the dominance of viscous over inertial forces. So, therefore, the first thing which happened, as I have said, that the gravity, the inertia is more important, or rather the surface forces are more important as compared to gravity. When surface forces become more important with respect to gravity, first thing, stratification suppressed, we have already discussed. It is very evident if you see this horizontal flow patterns, you can very well see that stratification is more or less suppressed. The other thing is, if you compare the flow patterns in this horizontal Milli channel with the flow patterns in the vertical Milli channel, you find that more or less the same type of flow patterns are evident. What do we have? We have dispersed flow, but this occurs only at a very high liquid and a very low gas velocity. At one particular extreme, we do not have dispersed, or rather dispersed flow is not very common in microchannels. Very frequently moment small bubbles are formed, they coalesce and they formed such type of disc shaped bubbles which are smaller than the channel cross section, but they are comparable to the diameter. Very frequently the bubble diameter becomes comparable with the channel diameter, as a result of which we have elongated bubble flows in this particular case. Now, for this elongated bubble flows also we find that people have used different names. Sometimes they say it is a isolated bubble regime, then they say coalescing bubble regime. So, lot of names are used. The basic thing is, when the bubbles, they they have very less tendency to coalesce, they flow as separate entities, then we call them the isolated bubble regimes, and when more or less they start coalescing and forming bigger and bigger slugs, we call them the coalescing bubble regime. The main thing which I should say is that for the microchannels, since we get very similar sort of distributions, but we understand that there is a difference and there is a need to differentiate this and this flow pattern. We do not have sufficient words, or in other words, not much information from macro channel flow can be used in this case. For example, both these two things, both of them are more or less bubbly, or what to say, your bubbly slug, etc., etc. But there is a definite difference between the distributions. So, how to differentiate them? Some people call it bubbly, some people call it isolated bubbly, because there is very less chance of the bubbles coalescing, and in this case they call them either coalescing bubbly or confined bubbly, because in this case it appears that as if the bubble, it has been compressed by the channel wall to take that particular shape and flow. So, therefore, the most of the regimes you find that there is a periodic sort of appearance which characterizes the slug flow pattern. And then we find that after this bubbly, confined bubbly, etc., the bubbles start getting larger and they assume the typical bullet shaped axisymmetric shape of the Taylor bubbles. We call it the slug flow pattern. From the slug, as the slugs, the Taylor bubbles start becoming larger and larger, so they come into each other's wakes and they start coalescing with one another. There is a portion where they are coalescing, yet there can be some liquid bridges. The liquid, they are so short, we cannot call them liquid slugs. They are sort of, they form sort of rings around around long Taylor bubbles. So, sometimes they are called as liquid ring flow. Sometimes these rings, they become larger in proportion, they form lumps which are again driven by the gas. People call them liquid lump flow, but basically they are different variations of the slug flow pattern. And only at very high gas velocities we get a situation where the gas is flowing at the center and the liquid is flowing as a core. So, dispersed bubbly and annular flow regimes, which are inertia dominant flow regimes, are very less, or rather they are not very frequent in microchannels. We continue with our discussion in the next lecture session. Thank you very much for it.